Just plugging things in, we should be good. And if I think we will do zip, righto. Let's see what we've got there. Cool. So this is the general outline of what I'm hoping to for us to have a look at this morning. This is of course morning for me. It's 5:45 in the morning on Saturday, and that's cool. So we'll once a few folks hop on board, and I see that we've got people watching. I'll go through what the current status is a little bit. In the meantime, I'm going to start hacking on some of the VHDL to improve the signal resolution when we're capturing data from the floppy drive, so that I can do more simulation. Hey, Anti-Magic Knight, welcome along. LGB, he says good evening or whatever Australia and other parts of the world have now. I can assure you, it's, I was going to say bright and early in the morning, but it's not even bright yet. It's just morning. It's starting to get light out there. It'll be light in a little while. Hey, Kit Canone, welcome along as well. So there's at least 3 of you watching, so let's have a look at what we have for the current status of things. So I'm just going to push make sure I have the latest bit stream on here. Anti-Magic Knight says, well, no one is here. When is it on sale? As I won't tell anyone else, promise. Yes, that's fine. I'm adhering to the same rule as well, and actually I don't know exactly. Hey Marauder, welcome along as well. Basically it will go on sale when the last preparations have been done to enable it to go on sale. As frustrating as that is for all of us, we're all excitedly waiting and wanting to see how quickly it sells out and all of that kind of fun stuff. Let me get the right command happening here. I've been running so many things here. Anti-Magic Knight says, you picked a bad week. I'm on a course next week. I'm not going to learn anything as I'll be looking at my laptop all day. Oh, you're welcome. Our work here is done. Hey Prowl, hey Lyden. Welcome along folks. So, actually I'm just going to make a quick change to the code. I need to change my view there, don't I? I've got one of those Redshift programs on my laptop, so for the first half an hour or so we'll have funky sepia tones on my editor here. Read track. Oh, that's MFMD code. We'll come back to that one soon. We're going to go to floppy test. Read track. So I had set things up so that whenever I was changing a setting, I was actually reading the data so that I could get the data out there. So I'm just going to disable that. Now Lyden was asking things about the time zone here. Yes, Adelaide is on a half-hour time zone. It's quite unfortunate. The rest of the world is disorganised and ends up being on a whole hour. But we're organised here. We're on a half-hour time zone. Interestingly, hey Amok, the border between South Australia, so we're in a half-hour time zone, and Western Australia, which is an hour and a half behind us on one of these uncivilised full-hour time zones. Oh, the music is a bit loud still, is it? Sure. Hopefully that's better with the music. No worries, and thanks for letting me know, because otherwise people kind of battle through without saying anything. And hopefully there's no hum on the music. I've fiddled with the gains from the laptop, and so hopefully it should be swamping any hum that was there. So let me know if that's fine. But yeah, so between South Australia and Western Australia, Anti-Magic Knight says, I'm too rude to put up with it. Yeah, and look, we're in a community that we have a lot of German kind of folks here, so feel free to be direct, as everyone else will be. Oh, LGB says, Paul, I'm just curious why the Emacs recently, if I remember you used Vim before. No, it's not a Vim Emacs. Flame War, I'm just curious. No, so I've pretty much always been an Emacs man, going back to the early 90s when I started at uni. I use Vi when I don't have the need or otherwise to pull up a full-on editor, but otherwise, yeah, Emacs is what I'm comfortable using, which very much dates me these days, as everyone else is going like, oh, you're using Visual Code Studio and all the rest of it, which is all fine and lovely. Anyway, so yeah, the border towns between South Australia and Western Australia, it's 1.5 hour time zone difference, and they're nowhere near Adelaide. So our time zone doesn't make any sense for them, and they're nowhere near Perth. Their time zone doesn't make any sense for them. And so they're on a 3/4 hour time zone, so they basically average the two time zones, and so it's Central Western Australian border time, and it's supported on some operating systems, but not all. And it's possibly the time zone for the least number of people in the world. There's about 400 people in the Central Western Australian border time. So they're on plus 8 3/4. And also I think might have been Nepal, or even North Korea or something. There was a couple of funny countries that disagreed with their neighbours, and so they just moved 15 minutes off just to be contrary. So yeah, and Prow is saying that there's a province in Canada also has a half-hour time zone. Yeah, look, if your zenith time is near a half hour, it makes a lot of sense, as it is for Adelaide. We like to pay out the folks in Melbourne and Sydney who complain about our half-hour time zone, and actually point out that their zenith time is actually closer to our time zone than their own time zone. So that's all fine. Anyway, back to the 8-bit fun. So I'll just disable reading the track because it just slows things down for what we want to do here, which is to have a look at just how much we can cram on a track. Now, I fixed a little bug in here where the way that the data rate was being written and read was out by 1. So it's possible that will slightly improve our read performance at these fine data rates. So we'll start again. So enable, I need to take that out. That's going to be annoying as well. It was part of that. Actually, I'll just put a hash if def around all of this. Hash if def read after format. This hash def is of course not defined anywhere, so we'll just disable that code. Kikanan is saying it's hard to be hyped until I find out if I have jury duty, and if so, whether it'll get in the way of ordering a MEGA65. Yeah, Marauder64 saying even if I have to be up at 3 AM. And yeah, it's great actually to see the excitement to get the machines. We are, as a team, super excited as well to see this all coming out as well. Amok64 has got his phone set to ring every time the pre-ordering page is changing every 15 minutes. Yeah. Okay, so this is good old MFM encoding with no write precompensation and at the normal double density rate. So I'll just disable formatting for a minute while we dial that back down to data rate 2.8, which is high density 1.44 meg standard rate. We're on track 0, so this will get the best performance of any track on the disk. So we can pull that down and we can see again we've got our list of sectors that are being found up there, that's getting 21 sectors on the track, which is great. Andy Magic Knight says my missus watches American football, so she'll be up most of the night, so I've tasked her with pressing refresh and I've trained the dog to fetch me quick the second she sees orders open. Excellent. Right, so if we'll now keep winding the speed up on the MFM encoding, so that's 24, sorry 20, because it's 0 to 9, isn't it? Right, so that's 24. Geez, so what's that? Yeah, so that's actually 22 sectors per track, sorry, at this, at the DD data rate. So that's as many as an Amiga fits, even though we've got gaps between the sectors. So now let's wind that up. If we get to about there, so now we're getting 26 sectors per track. But again, we're seeing the need for write precompensation, so we'll start dialing the write precompensation up. And I did find an actually useful floppy data sheet, floppy drive data sheet, a while back during the week, that actually said that 125 nanoseconds, so that's a 5 in the write precompensation, is optimal. And then we're tuning our thing to move the center peak. So that's cleaned up the signal quite a bit there, which is good. So now we can go onward with our march of trying to squish that together. And that's probably somewhere 1D, 1C is probably about the limit of where we can get with MFM, where it looks nice and reliable. So that's 30 sectors per track on track 0. So again, it will decay a little bit as we go to the outer tracks. So you could probably say in MFM with sector gaps, we can get about 28 sectors per track. So I should get my pencil out because we'll do a little bit of, again, quick calculation just to see where we're up to so that we can compare hopefully at the end of the stream. So if I press G to disable gaps, we should now get a few more. And again, we have to wait for it to find its way through. So the top row is 32. So that 0 on the bottom actually means 33. So that's no gap. Gaps is 28. MFM. And then we've got RLL 2,7. Right. So let's go and switch now to RLL, and it's quite obvious, right, when we switch to RLL, that we can see that the signal integrity gets much better. The peaks are much better resolved with bigger gaps between them. So this is fundamentally why RLL can do higher data density on there. So now let's wind it back. Now remember, the write precompensation doesn't work with RLL. That's something that we're going to attack today. So we can come back. Yeah, look, that's probably one step too far. So this is using a data rate of 1.8, and for MFM we're using 1D, right? So now with gaps we are getting 35, and without gaps we're getting 40 sectors per track. Hey, Volta Viva, welcome along. So if we do the quick bit of calculation as to what these numbers mean across the entire disk capacity. So if we get 28 sectors per track, and we know that we'll probably average about 26. You end up taking off 2 roughly to allow for the fact that the inner tracks are shorter and have more trouble. The nice thing is we can just multiply it out to 2 sides, and sectors are half a kilobyte each, so both sides means 1 kilobyte per sector. So we can actually just multiply out. So with MFM, with gaps, so that would be a disk that can be written sector at a time to be modified after, we're getting about 2.08 floppy megabytes, which is still not bad. And then if we say 31 times 80, so Amiga style formatting, we're getting 2.48. And now if we say that we can do 84 tracks, which the out drives tend to be pretty fine doing, we're potentially getting up to about 2.6 meg. And now if we go to RLL coding, we'll just say 80 tracks initially, 2.8 megabytes, which is just nuts. And that's only using 80 tracks. And 3.2 megabytes. So we can match the capacity of an FD4000 drive without write precompensation using RLL encoding already. And with write precompensation and read post compensation, assuming it works as well as I'm expecting it to do, we should be able to hopefully get up around maybe 4 megabytes or so. We'll see. But this is already pretty cool that we're getting up to those rates. So what I want to do next, so FPGA synthesis for this is taking 30 to 60 minutes. This is a little bit random every time. So we've got time to do probably a couple of synthesis runs if we need to. So the sooner we do it, the sooner we have it done. So the first one I want to do is to make it so that I can get the floppy pulses with cycle level accuracy captured really easily. So what I've been doing so far, so if we go, so here in floppy test, if we go to that read track routine, so this is the routine that I've been using to do it. And so what it does at the moment, there is a debug register on the MEGA65 that lets us read the exact state of the floppy read line. And so I'm doing a DMA with a fixed source address and just slabbing that down into memory. So each of those operations is reading from an IO register, so that takes 2 clock cycles on the MEGA65, and then it takes 1 cycle to write it out. Yeah, sorry, headline, people are saying this should be called Floppy Fantasies as an episode, and this one then is Floppy Fantasies 4, which is quite likely true. Anyway, so we do this DMA copy, and it takes 3 cycles to do each read. So we're getting a resolution of about 75 nanoseconds, which sounds well and good, but it's actually starting to interfere with the ability to tell what's actually going on. Well, I reckon we've hit a new record. We've got 16 of you fine folks on the channel now, which is great. Welcome along. Feel free to say howdy if you haven't already. Yeah, so what I'm thinking of doing is modifying the DMA controller so that the DMA controller can have a brain feed directly from the floppy drive and read that pulse register out directly. So that will let us get about 25 nanosecond accuracy. And if I do it right, I can actually make it so that it reads the gaps and waits between gaps so that we can actually get 65k gaps rather than just 65k samples, which will let us get multiple whole sectors worth of data, which will make it easier. Because then we can actually fiddle around with code on the Linux box to see whether particular algorithms are going to work for recovering the data more effectively at these higher data rates. Hey, CodeXWe, welcome along. So that's my thinking. So what we need to do is SD card IO .vhdl. This is the VHDL that actually does the floppy controller. And we have, I reckon I already export magically somewhere the most recent gap. I think it's just to a register, right? Recent gap. FTC last gap. Here we go. And so it only gets the bottom 8 bits of it. That's actually fine by me, because at these high data rates, we never have an interval more than 255 cycles. So the trick is we need to know when that has been changed. So in the MFM decoder, MFM last gap. So we export last gap. Right, here's where we output it. MFM last gap strobe. So we're going to, because we need to only do it when okay, right, so in the upper bits we're putting gap count. So that's how we can tell whether it's changed, which we're doing in here. If Q gap count, so where is gap count getting set? Let me just gap count. So the Q gap count is a quantized gap count. Okay, gap valid is what we want here. Gap valid. We're probably using it for something already. Not much, right? MFM gap length. Isn't that what it was called? What was it called? Oh, MFM last gap. Right. MFM last gap strobe was just gap valid, wasn't it? I reckon what we had. Yes. Okay, and so we need MFM last gap, MFM last gap, strobe out, stood logic. So we're just copying that signal directly, so we're just going to make sure that MFM gaps sets that gap valid for one cycle at a time. Gap valid. Yeah, so it gets set for exactly one cycle, which is what we want. So that's getting it exported now into gap. MFM last gap strobe. Yep. Okay, and we had that exported here. Right. Okay. So now we want to go back into SD card IO. MFM last gap. MFM last gap strobe. FDC last gap strobe. Hey, them 3WP, welcome along. Well, it's the M3WP, right? Yeah, someone stole my nick, so annoying. Indeed. But welcome along anyway. Okay, so that's now got our signal available to us here. So now we need to export it. Now I could export the signal directly, but I'm actually going to put a drive stage in because it will just help the timing, because this is going to go into the guts of the DMA engine, which is already under a bit of timing duress. Direct export of floppy gap timing info. Floppy last gap out unsigned 7 down to 0. Floppy gap strobe out stood logic 0. Right. Come down to the clock. Floppy last gap gets, what was the blasted signal called? FDC last gap, I think, wasn't it? Yep. Hey, old school caller, Coda, working along. You're saying, is the C? I missed what that was about, I think. If you're asking about the programming language here, this is the VHDL for the FPGA. Floppy gap strobe, FDC last gap strobe. Export last floppy gap info, so that we can have a magic DMA mode to read raw flux from the floppy at 25 nanosecond resolution. Right, so that's an SD card IO. That comes into IO mapper. So we need to export it here. Floppy last gap. Yeah, the test program was in C. That's right, but now I'm modifying VHDL for DMA to read from the floppy. He just said that. Right, so that's what yeah, MW3P was saying. Which is cool. Floppy last gap. Whoops. Floppy gap. Strobe. Floppy gap. Strobe. Right. So now we need to add it to the export list here, which we can do floppy gap. So to save a bit of typing, if we use exactly the same signal names, I can just export that through. There's one thing I hate, the VHDL mode in Emacs. If you hit tab in the middle of something, it tries to complete it without realizing you're in the middle of a word, which is quite frustrating. Right, so that gets it out of IO mapper. And then the IO mapper is here. The machine, so we need to do as we did in there. Oops, haha, good thing I spotted that error. I would have a here's what we want to copy. And then we have GS4510. Here's our CPU, so we need to plumb it into the CPU as well. And then we need signal floppy last gap. You're probably getting just a hint of just how verbose VHDL is. We're just trying to route a couple of signals between two units, and there's a lot of typing. Okay, so now we can go into GS4510. Actually, we need to get the, oops. Come at the top and now make the input path for those signals. Block, 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 block. Okay. And now they won't be outs, they'll be ins because we're reading them into the CPU. Right, so we should now have the floppy signal is available to us with 1 cycle delay, but with only one, with you know, the update rate of that is cycle by cycle. So let's go DMA fill. We've already got a pause. This is good because what we're going to do is to pause the DMA until we see a strobe on there. So if we do a fill, we're going to have a magic mode for this. Oh yeah, and you can see the those who remember the Shalon spiral. This is the VHDL for the Easter egg of the spiral mode that I added in. Yeah, so M3WP is saying, oh, it takes a cycle to propagate the signal. Interesting. Well, so I've set it up to take a cycle. So whenever you latch something on a rising edge of a clock, that adds a cycle of latency. But that's fine because it's getting latched at each cycle. So it can change every cycle, but you know it takes a little while in the pipeline to come out the other end. So we're literally pipelining the floppy signal so that we can have it at the full accuracy in the CPU. So let me. So we've got the reg dmagic. Where's the fill value? So normal fill. Because we do. Old School Caller is asking, so are we coding for the actual hardware or emulator? The answer is yes. We're coding the VHDL, which will get synthesized into the FPGA, but we can, in principle, do the to run this under simulation. In theory, the change should be simple enough that we shouldn't need to do simulation of it. It'll either build or it won't. Aha. If pending DMA busy is 1, right, so this is where we check if we need to pause for the audio DMA. So if DMagic floppy mode is equal to 1 and floppy gap strobe is equal to 0, state DMagic fill pause for floppy wait. So we'll add an extra state in for that. And we'll tell it to unpause. Oops. Let's see whether I've missed any of these floppies somewhere when we go to build it. Floppy gap strobe is equal to 1. Resume it. And I think then all we have to do is change the value that we're writing out, which is the upper byte of the DMA source address. Oscar Collar says, looks just as frustrating as VS Code with auto completion. Lol. Yes. So get updated floppy gap value into the spot that DMagic will use as the fill value. Right. So now we just have this floppy mode. We need DMagic floppy mode. Signal DMagic floppy mode. Oh, we should have reg on the front because that's how we're doing them here, right? Cool. So this is our option codes for single byte options. So we need to have an option that lets us enable that. And we'll use option 0F for floppy. Reg DMagic floppy mode. Now what I'm looking for is that we clear the floppy options somewhere. I'm trying to find, maybe we don't. Here we are, DMA magic reset floppy reset options. So reg DMagic, and we weren't resetting spiral mode. But let's just get that one right first. Reg Magic. Draw spiral. Reset. Reg Magic. Draw. Yep. So we'll clear that as well. That should be fine. Yep, we're clearing the transparent value as well. You can actually see that the line mode for DMA has lots of options there to do the line stuff. It's actually it's quite complicated. Really nice that we've got it in there, but yeah. Yeah, Andy Magic Nice says, I bet the DMA spiral wouldn't come up pathetic second place. Yeah, I think we worked out that you could do a using the DMagic option, you could do the spiral code in like 38 bytes or something crazy. But of course, it's completely cheating when the hardware has direct support for the exact challenge. Right, so I think that has what we need in there. So let's get this happening here. Git diff. We should always commit our git changes before we get any further, and there's always random byte space. Okay, so that looks to me to be good. Git commit-a implement DMA assisted reading of floppy flux, and we'll have that under 442, which is our issue for the high density floppy stuff. Merkbit, that's just a script that I have set up to make life easy. So that will chug away in the background and work on the synthesis. And in the meantime, we can have a look at the write precompensation for the floppy. And so if that fails, when it finishes, that will give me a big visual alert, because that can take, as I say, 30 to 60 minutes. So let's go into RLL 27 bits to gap. So now we want to do the write precompensation. Time adjust. So this is the value that we have. We can adjust the time that it writes the bit from the nominal transition point. And the VHDL synthesis has failed, so there's probably a typo I've got in there. Let's see what that is. Synthesis has failed. Floppy gap strobe is not declared in SD card IO.vhdl. Okay. Floppy. Okay, maybe that's one of those things where I've got the floopy. Yes, it is. Have I got any other ones? Yes, I do. Right. I think I even misspelled floopy in the commit message, but that's fine. M3WP, are you using the free Vivado? Yes, I am using the 3 Vivado. And in answer to the question, no, Shalon didn't write the VHDL for the spiral. I wrote the VHDL for the spiral as a surprise for Shalon. Yes, so the thread count is limited, but that's okay. My laptop has a hardware limit on threads, which is distressingly low as well. It's a i7 with 2 real cores, so 4 logical cores, so that's fine. But as you, various stages of it can't parallelize very well anyway. I can't remember which particular stage, whether it's place and route has trouble. And I think actually with lots of threads, sometimes all it does is it tries different random number generators for it when it's trying to do the place and route, because there is a lot of random decision making that it does to try and do the place and route. And so I think it just tries multiple ones at once and hopes that one of them will finish before the others, which is quite possible. And indeed, it's bombed out again. So what have I got wrong then? Oh yeah, I didn't define this. Red, yes, Dear Magic Fill. Oh, we should capitalize it nicely, shouldn't we? Not that it matters. So VHDL is case insensitive. It's paranoid about just about everything else, but doesn't care about case. Okay, let's try that again. Where are we up to? So now we're trying to, that's right, the right pre-compensation for the for this. So the time adjustment is the advance or retreat of when we write the pulse. Because when you write, it's a reminder for those who haven't followed along on this previously, when you write pulses near to one another in the magnetics on a floppy disk, they can either end up squished together or spread apart, or like basically things move around because of weirdness with the magnetics. So some of it is actually how long it takes for the write head, once it's changed magnetic orientation, to overcome the flux from the previous pulse and the previous data written further ahead on the disk. So that it actually starts saturating the flux on the disk and changing it. I don't understand most of it still, other than to know that it's a complete horror. So anyway, what we have, time adjust. Right, so if we have no write precompensation, we do nothing. If we have it enabled, and you'll see here that I've got my note here saying I need to implement it, in all other cases, do nothing. So to give an example, bits to gaps. Here's what it looks like for MFM. Yeah, M93P says, yes, the horror. I studied a bit at uni and hated it and remember nothing. Yeah, the magnetics is bizarre. So what we do, the middle bit in this buffer is actually the bit that's about to be written. And so it gives us a look ahead and a look behind of what's being written so that we can decide what we need to do. Because as I say, what's happening either side will affect whether this bit gets shifted a bit left or a bit right. Well, a bit of a bit. Oh, and the VHDL synthesis has bombed out again. So let's see what I've got wrong now. That's how we know we're alive, right? Okay, there will be a single. Okay, width mismatch. SD card IO 1647. This will be when we're taking the gap length, I reckon. Because it's 16 bits. Yeah, so we just want the bottom 8 bits. What we might do is a little bit of safety. If FDC last gap 15 down to 8 is not equal to 0, then floppy last gap right. So basically we'll know if a gap is really long rather than getting utter nonsense out of it. Okay. Fix floppy gap width mismatch. Okay. That's running again. So back to trying to look at this. So we need to do something similar for this. So we've got two different right precompensation magnitudes based on whether the pulses are really near to each other or not so near, so that we can tweak different things. And the trick is with RLL, instead of there being 1 0 between, there are 2, but we're actually running at a higher data rate, so that as far as the magnetics are concerned, it's the same thing. But it means that we need to retwiddle this. RLL 27 bits to gaps. So we'll paste it in here. Now what we're going to do is we're going to make these sequences 2 bits longer. So I need to change some other magic further up. Okay, so we go from the top. So there's 2 zeros in a row is the shortest gap we can have. So what we need to look at is where there is either no pulse in that nearby range, whether there's one the nearest it can be, whether there's one of the furthest it can be and still in range, or whether there is none. So the number of cases we have to consider is the same, but they just have to be longer. So we need to change F right buff. And we've made it 2 bits wider. So where we pull it from the middle will now be bit 4 instead of bit 3. And the whole thing is 2 bits longer. And we've still got those plumbed through, so that's looking good. Now, git diff. So there's our changes. So git commit -a, implement RLL27 right pre-comp adjustments. Right. So that's our right pre-compensation. Actually, what I'm going to do, because we've only just started the synthesis, rather than having to wait 2 cycles to get that finished, I'm actually going to stop it because we've only lost a minute or 2, right? Well, 3.5 minutes apparently. So we'll get that running. And hopefully that will chug through just fine. And while that's running, we can have a look at the read post compensation. So this is me thinking about better ways to improve the performance of the reading. So if we come back to here, I'll show you what I'm trying to fix. So if we label formatting, right, so we're back, what's that? That's better, yeah, the TIB has been updated. Okay, so this is MFM and double density data rate. Interesting actually, there's a little bit of poop, those short pulses there, that might be end of. Oh, I'm not sure what's causing that down there. It could be that if when some of the pulses are too long, the floppy logic actually doesn't cope very well. And so you start getting rubbish as I make it slower. You'll actually see that we'll start getting more of this rubbish with these low pulse rates, and it might actually be that that's just wrapping around 255 as well with the way that I'm doing it in here as well. But as we increase the writing rate, are we on which? Oh, we're on a high track number, and that could also have been causing some dramas. Oh, and our VHDL synthesis is balked, so I've fluffed something up. Let's have a quick look at that, since that's critical path for us. Right pre-comp delay 1.5. Okay, 160. Oh, okay, let me have a look at that. Delay 1.5. Whoops. Yeah, because this is the extra coefficient I added in for moving that middle peak. Get that synthesizing again. Okay, so where were we again? We were. Oh, that's right. We were looking at this. Oh, that's the wrong button, isn't it? Oops, if I don't hit the fade to black button instead of the transition button. Okay, so we have these pulses, and we can see that they're quite nice and narrow. If I just freeze that for a moment, where's my right? And if I nope, that's not what we want. We don't want to see my noggin. Yeah. Okay. Because then I can point at these peaks, right? So the peaks are quite nice and narrow. If we look, I mean, compared to the keyboard, right, it's fitting between the edge of the V key and the printing of the letter. So if I unfreeze that and let that update again, and we start pulling the timing back, so we can already see that it's getting a bit fatter at the high density rate, that the peaks are spreading a little bit wider than the printing on the key. Whether we look at the V key again, since we know that that will be the same apparent size, it's a little bit wider, and we can see here that the first peak is actually noticeably wider again. And then as we start winding it further, we can see now they're really getting fatter. It's not just that the timing is an issue, but the pulses are now like seriously fat. If I actually bring that a little bit further over, see that this third peak, you can actually see now here at V, it's most of the width of the key. But we see these three resolved peaks, right? So this is what the right precompensation fixes. So we can compensate for that a little bit. We bring up the coefficient A and coefficient B. And we can see while we haven't fixed that third peak, we have improved these two peaks. We can also see this gap again between here is not even. So that's what this coefficient lets us do, is move this center peak will move to the right so that it's equally spaced between the two. But generally speaking, the higher the data rate, the wider those peaks get. So what we're talking about in reality here is that the uncertainty of the timing goes up as we go to higher data rates. So it's not just a case of the gaps between them get smaller, so we have to be more careful with the differentiation. The slop in the signals we're trying to read, because of all of these magnetic horrible effects, is making it harder to resolve. And it's all because of, so the gap from the left of the screen to here, that's the duration of the shortest pulses, and this is actually what causes the most problem. The nearer the pulses are together, so the further to the left, the more messed up they are, and the more they will mess up the other pulses. So if I hold, right, so that's about on the right edge of the X. If we switch encoding to RLL, what you can see at the same data rate, so the secret sauce of RLL is that it makes all the pulses be, as we saw, instead of being 1 0 apart, they're now 2 zeros apart. So it's 3/2 because the 1 bit counts in there as well. So the pulse widths are back to being skinny again. And it's only as we start winding it back and it starts coming back closer. So again, so interesting to remember, with MFM, we could come back to here, to the right edge of the X character. But what we're seeing with the RLL, because we don't have right precompensation yet, and that's what we're synthesizing at the moment, we've got the triple peaks on each of them again. So that's spreading the peaks, and again, it's these first two where the two relatively shortest gap lengths occur, get the most interference. And as you head across to the right, it's actually fairly well resolved. The bit of fluff that you're seeing here occasionally, that's the track information block marker, and it has 3 peaks because that's written at the DD rate in MFM always. So you can just ignore that that's occasionally appearing in there. So adding the right precompensation should let us bring that further back to the left. But we should, so all going well, if we manage to make things fantastic. You can see here that this is really breaking down at the moment because it's having endless grief. And in fact, the display up here showing the number of sectors that we're reading, it's stuck showing the last sector that it read from a different track. So we're not getting anything, but in theory, we should be able to use a data rate of $1.12. So that's 18 instead of 24, which is what we've managed to get with a data rate of 1.8, which was working. So 1.7, in fact, is also kind of working already. 1.6, in fact, is kind of... So any of these that are kind of working with the right precompensation, we should be able probably to get working fairly robustly. And then down at rate 1.5, of course, it's gone completely to mustard. But remember, at a rate of 1.8, which was 2.4, right? More the point, if we say 40.5 megahertz divided by, so that's the tick rate of writing to the disk that we have at the moment with RLL. With MFM, of course, we were limited to 1D, which is 1.39 megahertz. So again, because these are divisors, each little step that we go down now is making a bigger difference. So if we do 40.5 megahertz, and if we could actually get down to $1.12, which has the shortest gap interval actually the same as what it is on MFM, whether we can quite get that far, who knows, but that would get us 2.25 megahertz for the bit clock, rather for the floppy transition clock. For reference sake, that's faster than what an ED floppy drive ran at. ED floppy drives ran at 2. 1.44 meg floppy drive HD is at 1. and DD drives are at 0.5. So we're already at 1.68. You know, we're on average, and of course it will be a little bit less on average because the higher track numbers are not as friendly to us. We're already nearer to the ED data rate than the DD data rate, but I think we're going to have a decent chance of getting up to the ED floppy drive data rate. So to do that, we need to get to a divisor of $14 instead of $18, because that gets us to 2.025 megahertz. So that would be a really nice thing. And so, as we'll actually see in a minute, what's enabling all of this is actually that the ALPS drives, at least, and most later 3.5-inch floppy drives have much better timing accuracy for the motor. Like they hold a constant data rate for the motor much better than what the earlier drives could do. And so that enables us to use RLL encoding, which needs more accurate timing of those gaps once we get rid of those other kind of effects. Now I was just checking because I thought someone was saying something on Discord that was of relevance. No, that's right. I don't think there was anything that we needed to respond to there. I think folks have got access to the chat here now in Twitch, all right. Although you're being notably silent at the moment. Cool. So let's have a bit of a look then at which one is it? Yes, right. Okay. So first up, our synthesis is still running. That's good. So let's now hope there's probably a decent size font. So what I've been looking at now, and this is the reason for trying to do the accurate data capture from the floppy drive, is that we can on Linux simulate different methods of extracting the pulse intervals so that we can try and pull everything in terms of the width of those peaks to get them narrower. So what we have at the moment for the phase locked loop is quite crude. So in fact, if we have a look at, come on, quantized gaps. So this is the thing that decides which of those, so this is the MFM one, right? Is we want to know whether it is the first peak. So in MFM, they call it the 1.0, the 1.5, and the 2.0 peak. So we're calling them here 10, 15, and 20 because we can't have decimal points in variable names. We just have simple thresholds, and for each gap coming in, we check which of those thresholds it seems to fit into. Yeah. So in terms of the chat, so Old School Caller saying, yep, still here, and Andy Magic Knight saying, brain fried, can't think and type. And this is can't think, to be honest. Yep, no worries. That's all right, as long as you're going fine, but if it's boring, let me know as well, right? So what we are doing, if we go back to, right, so if we have pulses coming in, I'll just put some full stops so that we have a bit of a reference so that we can count things. So if a pulse is supposed to come in, say, every 5 cycles, cool. Yeah, Old School Caller, glad that you're not finding it boring and rather finding it fascinating. Hey, Herdware, welcome along as well. Right, so imagine that we're trying to read this pulse stream coming in. And you go, yep, that's all good. So we'll do another version here under it. So our pulses are coming in nicely, and then this one's a bit late. So what we have now, instead of 4, 4, 4, 4, 4, we have 4, 5, 3. So this one being late is actually messing up the next one. And if, for example, we had that, then we've got 5 and 2, and so it's all going to be a bit of a problem. So what we want to do is, in the very least, so this one's a 4, right? And this one is being then read as a 6, and this one's being read as a 2, and then we're back to reading as 4 again. We want to figure out when these late pulses are happening and not have it mess up more than itself, and we want to be able to to correct these as much as possible. So in the very least, we should read that as that, right? So that third pulse wasn't delayed. It should be a 4, because we can actually tell, if we go back a couple of pulses, we can actually see that it's in phase for it being a gap of 4 across all of those. Now, if, for example, we had some effect that was causing multiple pulses to be late, it would be nice, again, we should be able to say, well, that one's in phase with all the others normally, so that's a 4. And this one, we should be saying, hey, well, hang on a minute. Yes, it looks like a 6, but actually it's in phase to this other one back here. Hey, Marauder, and thanks as well for affirming that it's interesting. So we could even actually say that this one is a 4. We can't do much about that 6 at the beginning, because it's just nothing that has given us any warning that it might be late. So what we're doing, what I've just described here, that would get us to this stage, is a hypothesis phase locked loop. Hey, Dr. Holken. Yeah, good tomorrow, he says. Excellent. Welcome along. Where we have multiple hypotheses for what the phase of the clock is. Because if you like, the magnetic who's a what's is causing phase drift and phase smear among the signals. And so what we want to try and do is to be able to pull as many of those up correctly as we can. And there'll be the odd one that we can't deal with, but hopefully they'll be rare enough, certainly rarer than, again, if we look at this situation, if we didn't do that, we would have 4, 6, 2, 4, 6, 2, 4, 4, 4, 4. And if we imagine for a moment that, if the 4 is for a 1.0 pulse, so if we're using the MFM, right? Then 6 would have appeared to have been a 1.5, so that would have been misclassified, and then this would have been a 0.5, and go like, what the flibbits is that? 1.0, 1.5, another 0.5, who knows what's going on with that? 1.0, 1.0, 1.0, 1.0. So we'll have totally misdecoded that. Whereas with the multi-hypothesis one, we can say 1.0, 1.5, okay, we couldn't resolve that, but then all the rest of them will actually be correctly classified as being 1.0 long. Now, this is a bit extreme because I've made it quite narrow. In reality, there are many steps in between, and the drift is less. But again, if you get something horrible where, say for example, this one was early and that one was late, now you just go, oh, this is terrible, and we start misclassifying. So I'm trying different approaches with a multi-hypothesis PLL correction algorithm as a read post compensator to try and squelch these errors out. And the interesting thing is going to be to see whether it can actually work. So if we come back to here, I need to get the right command. Oh, pardon me. Magic happening here. I've made a little program called MFM decode, which actually can do RLL as well. And this is just another one of these hacky little tools that I've been evolving continuously as I work on things. So let's have a look at RLL 0. So this is going to go through and read all of the data off of the track. And what we should see, so I've made it clever so that it can identify the track information block, and it looks at the divisor and the encoding and goes, this is now an RLL track with this divisor, so it sets the frequency to that. So this one was recorded data rate 17 hex, so 23 decimals at 1.76 megahertz, so 1 3/4 times the speed and 87 something percent of the speed. Yes, it was 87% roughly of the speed of an ED drive data rate, and almost double that of an HD 1.44 meg drive. Right. So as we go through, we have our uncorrected gaps, and I've been trying various algorithms in here. If we jump down to the bottom, what it's also writing out now is this handy file raw gaps. So down at about, we have to find the spot where it detects the switch to RLL, which should be about here. So the RLL encoding uses a different terminology. M3W saying, how long do you think your poor disk will survive this punishment? Well, I'm purposely using the same disk repeatedly so that if it's degrading, that then we're just getting more tolerance in the thing. It's actually been holding up really amazingly well. I think partly the ALPS drives, as a very late model 3.5-inch floppy drive that we're using, are actually really good drives. So this is actually helping a lot of it. A lot of this wouldn't have worked on the cheapest, crustiest drives that were available back in, like 1986 or something. So some of it is actually using better bits and pieces. Right. So we have the sync pulse for RLL is using the notation in this file, 8, a gap of 8, and then a gap of 3, and then a gap of 3. So we have, and there should be 3 lots of that. So again, this is using a very aggressive data rate. This is faster than what we actually have stably decoding, right? So without funky correction, we're getting 8.35, 3.52. So this is a problem, right? Because this is going to be rounded up to 4 if we do simple rounding. And then 3, so that's fine. And then 8, 3.26, 3.31, 8.22, 3.39, 3.26, that's all fine. Now because before this, we've just got random goop coming in, which is actually part of why I think we're getting this funny 3.55. But that's right, we still have to deal with it. Yeah, Judge Strock is asking, will disks survive the punishment? We'll find out. And this is actually part of why we've made it so we have the track info block on these disks. So you can actually have a disk for the MEGA65 using either MFM or RLL and any data rate you want, and the track info block tells the floppy controller in the 720K data rate MFM, which we know is solid as, what that track is. So every track, every side of each track, in fact, actually can be in a different format. So we might even end up with format tools that will try and work out just how good is your disk at different rates, and I think people will have lots of fun seeing just how much they can squeeze out of singular good quality disks. Anyway, so back to the point here, right? So if we want to decode this stuff, so the 3.52 is a problem. And even this 8.35, this is getting pretty close to being, halfway to being a 9, right? Although we actually, anything bigger than an 8, we can count as an 8, so that doesn't worry us. It's the gaps anywhere between 3 and 8. We need to have these clear division points to separate out the gap sizes. Okay, so 8, 3.523, 8.09, 3.26, 3.13, 8.22, 3.39, 3.2. So this is our 3 sync marks. And then we have the actual data that we're trying to decode. And again, this is at a very aggressive data rate with no right precompensation to save us from the horrors of floppy magnetics. And so, it's not surprising me that we're getting quite bad values out of this. Now, what I would need to do, we should ideally compare this back to a lower data rate to see what those gaps should be, so that we can actually see whether we are correctly decoding at the higher data rate with our new clever fancy pants encoding. This column is the current state of the advanced multi-hypothesis PLL lock. Right, so Judge Jock is saying, will this development hopefully lead to a new MEGA65 disk format that could be used as a carrier for digital versions on the SD? Yes, so we already have most of the support for D65 images in there. So D65 disk images, and they allow 85 tracks times 64 sectors per side. So it's about 5.5 megabytes. Unless, of course, I manage to get suspiciously close to 64 sectors per track doing this work, which it'd be interesting. In which case we might need to make it allow for 80 or something, which would nicely actually make a 6.5 megabyte disk, which just kind of sounds good. The trick will be then when you want to take it from the digital form and put it onto a real disk, is that you'll need to basically look for empty sectors at the end of the track and go, right, okay, what data rate can we write this out at? And write it at the lowest data rate possible to make the disk as reliable as possible is probably the way that might work. Okay, so we know that we have 833, 833, 833 is what we should be getting. And again, look at how mushed up this one is. Now I'll explain a little bit more of the columns of the data we have here. So this is the number of cycles, basically, with the DMA right between the gaps. So it's basically divided by 8 at this data rate gets you the thing. So 64 divided by 8 gets you 8. So this most recent gap has a duration of 8 or near enough to 8. It might be, might not be exactly 8. It might be by 7.5 or something funny. Anyway, so you can see here that these numbers scale directly with the numbers that we're getting for the thing. And then these next 8 columns, should be 8 of them, yep, is benchmarking the most recent gap, winding back to the most recent gap, and then going back further gaps to try and baseline, to do this multi-hypothesis matching, versus going back 2, 3, 4, 5, 6, 7, 8, or 9 gaps as that benchmark, and knowing how long those gaps are in between that we've quantized them to try and correct for everything. But at this data rate, this is part of why I'm doing that DMA funky thing, is that we actually don't have the accuracy to really be confident. We need to get from the 75 nanosecond accuracy down to 25 so that I can really see what's going on. So we should have track 0, because I started standardizing these a little bit more. 18 RLL dot dat. Okay. Okay, so here is at data rate 18, and so this is a much newer capture that I did. And so we can see, so this is, again, the naive one here. So it's 7.75, 3.0, 3.0, 7.75, 3.0, 3.12. Interesting. So a difference of 0.12 is currently the resolution of that DMA capture that I'm doing at the moment that takes 3 cycles. So we're going to be able to, after this synthesis is finished and I patch the tools and everything, we'll be able to get accuracy down to like being able to show 3.04. So this is going to be really helpful for us to improve what's going on. So now with the other various bugs fixed, the multi-hypothesis tracker, we can actually see is doing a much better job. And okay, this is at a slightly lower rate, and we'll have a look at the higher data rates in a moment. So here we can routinely see that there is stuff after the decimal point, and it's not, totally sure. Whereas if we look down this side, we're able to, at each cycle, one of the hypotheses at least is matching exactly, because we tend to have pulse shift. The clock is not drifting very much because these floppy drives are really accurate with the motor speed to within about 1%, in fact often better than 1%. And so here we can actually see, so we've had some shift at this one, right? Because we can actually see, if we went for a majority vote, we would actually go for the 7.75 that the naive approach has gone for. But we can actually see, if we reference it back far enough, we're actually exactly in phase with another one. So we can actually say, yep, we think it's 8.00. Here, we've shifted back to being in phase. So there was a pulse that was shifted, and now we're back out of that being shifted. So as we were showing on the diagram, this happens, right? So now we've actually got 4 of the 8 hypotheses are actually voting in favor of it being 3.00 long. And so what I've actually implemented is, if we count up the number of exact matches, and the exact match that has the most hits we take if there is conflict between them, right? Otherwise, we average all 8. So this is basically estimating the phase to be averaged based on the phase over the last 8 gaps. And as we're saying, this works pretty darn well. And the reason we're using 8 is we can do a shift by right to divide by 8 if we need to do this in hardware. We can add up the 8 numbers and divide by 8. So we've got, perfect, even though here on the left in that space we've had 4 of them wrong. Okay, here's one that we couldn't correct perfectly, but by averaging over the past 8 to estimate the phase, we actually get closer. We've reduced the error from an error of 0.12. Now our error is 0.06. We've halved the error by being able to do that. Now, it won't always be that fantastic. So the next one where we have error. So look, so here's a great one, right? Remembering that if we got up to 3.5, we can't tell whether it's a 3 or a 4 because it's split right in the middle. So 3.25 is starting to get closer to that, but we can actually clamp it because we can say this is exactly in phase with an earlier clock that we saw, even though there's lots of shifts along the way. And some of them are quite bad shifts. Right, so we come down further. Again, here's another one that we've fixed up nicely. And then there's some more that we've fixed up perfectly. We've got rid of that delta. If we come down. Okay, so here's the first one where it's actually made things worse. Because it can't tell. There's no exact match to that pulse. And so some of these, so have a look at this one. So this is a 3 and a 5. So it's possible that right precompensation will help some of these. So this is surrounded by 2 longer pulses, and this is actually known to cause dramas for the poor old floppy drives. That so this 353 sequence and then 354, both of those would be subject to right precompensation. And again, we have more here that have been fixed up nicely. So that's all good. So let's have a look at what that can do. If we go up one speed grade, is it still able to do this? So we need to come down to where we get to the 8. Okay, here it is. Okay, so this is with a divisor of $1.17, so this is faster than what we currently do. Hey Shalon, welcome along. Yep, by all means, lurk as you see fit. Okay, so this is, so the uncorrected was 7.7, so that's getting quite concerning because 7.5 we wouldn't be able to tell. We can turn that into 7.87, so that's actually, you know, it's reduced our error from 0.3 to 0.13, so our error is more than halved. The 2.87 we've actually directly corrected. You can actually see that there are 2 votes in favour of it being exactly right. And interestingly, actually, if we look at that previous one, that phase actually suggests that the previous one could even have been a 7.96. We could go even more complicated with doing some of this kind of maximum likelihood, further, you know, more complicated hypotheses, but I want to avoid anything that's going to be a pain in the backside to do in the VHDL. Okay, and so this one's got slightly worse, but 3.15, we can tolerate that. Look at this one, right? This would have been, this is right on the edge of what's feasible to capture, and we can lock it up to a 7.82, which is really helpful. And then this one we perfectly corrected. Okay, this one's a bit worse, but we can kind of tolerate that. And then again, look at the next sync mark, quite on the edge of what's possible to detect. And yeah, and so then we're getting good corrections down here. Okay, this one's a little bit worse, but it's not making it particularly bad. 3.26, 3.17, that's good. Okay, this one's marginally worse again. And this is again, we're having the higher accuracy will actually help us to see whether we're really fixing things or making things worse. But then look at this. So here we've got a whole bunch of phase jitter with these pulses being moved around quite a bit, and we're able to lock them exactly to 3.0. So this is giving me good hope. Here's another one that's just a stinking pile of turd originally, and that we've been able to by doing the averaging method, we're still able to improve it quite a bit. And again, this is before we implement the right precompensation, which again, 335, that's going to be subject to right precompensation. So I'm hoping that the right precompensation will help this quite a bit, and then that this algorithm will help it further. And again, look, here's another one, right, where it's halfway between the two, and we're able to resolve that fairly well. So let's have a look at the next speed up. Right, so this is going to be much worse, right? Because again, each time we increase it by 1, we are really increasing the actual clock rate by more. You know, the difference as the divisor gets smaller gets bigger. Okay, so here is our set of 3 sync pulses again. So we had 7.77, 327, 314, 764. That's pretty yucky, right? 286, 327. So it's quite bad. We've managed to improve that one. That one we've fixed completely. This one, okay, we've made it a bit worse, but it's still acceptable. That one we've fixed completely from being a complete horror. That one we've got much better. It's effectively, you know, almost no error. Okay, this one is slightly worse, but only slightly worse. This one we've fixed up quite nicely as well. and this one is a little bit worse. And again, some of these ones that are really bad at the moment are the ones that are going to be improved by the right precompensation. So, and that will fix some of the flow, the bleed error, right, between some of these things here. Because if you add up these, you get to almost, like, it's much closer to 11 than what the components add up to. And it's interesting, to see how that will kind of work out. So, I reckon that algorithm has a good chance of working. So what I need to do now, while that synthesis run is still chugging along, which it is to start implementing this algorithm in VHDL. And it needs to be able to run with very low latency, and it needs to get fed the unquantized gaps, and it just needs to know what the expected data rate is, so that it can try and hold on to that. So this will only work for drives that have fairly accurate timing, because otherwise, it will be a problem. So let's start making a read compensator. Now this will work for MFM as well as RLL. So we might just call it floppy read, or what should we call it? Floppy read compensator.vhdl. Now, VHDL is a pain in the bum to write. We're just going to copy boilerplate from the top. We're going to munge it. I'm going to call it floppy read compensate. Right, so what we need to read in, indeed, the cycles per interval. We get a gap in, and we feed a gap out. So this is all fine and good. And we'll actually have a correction enable line, so that we can basically decide whether we want to do it or not, right? If correction enable is equal to 0, what we need to do, if rising, okay, blah, 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 and I've forgotten more boilerplate here, we need to have a process, right? And it goes down here. Okay. So if the correction is not enabled, then this unit is really simple. Gap size out is equal to gap length. What? Oh, hang on. We need to change this, because here we're working in raw gap lengths. And VHDL, you can't have a semicolon on the last thing in the parameter list. It is... That was just... I don't know why. Anyway. Right. So we just work in simple pass-through mode. So simple pass-through mode if disabled. Right, so we need to have signal gap 0, I'm sorry, 15 down to 0, So this is our history of recent gaps. And then we want to signal. We need to know, because we have to quantize the gaps. So we need to know when the gaps came through in the past. So that's probably, we should call it gap time. And then we need to know for each of those gap quanta. And we don't need anywhere near as many bits for, well, it probably doesn't matter. Right. Now, we don't want to add a full-on divider in here. We want to do the division as efficiently as possible. Oh, now that looks like we might have a bit stream finished. Cooking in the oven. We do. So let's see if we can use the right precompensation on RLL to get some immediate gains, and then we'll come back to that. Here's my command. Two, 6, 9. Right. Okay, we'll get back down to track 0. Anyone want to try and make a speculation as to what data rate we'll get working with just having added the right pre-compensation to RLL, but not yet the read compensation? So we had, without right pre-comp, I think we agreed, let me wind it down, I reckon. What did we get it down to? Look at our baseline so that you can then make your guesses as to how it's going to go. So definitely 1.8 we were able to do, right? And I reckon 1.7. So let's call 1.8 was the best that we got with clearly resolved peaks. So there, I'm going to say that that's not resolved enough because the first two peaks are a little bit too close to each other, right? So anyone want to make a guesses as to how far we might be able to get with reasonable resolution of those peaks if we start turning up the right precompensation now for RLL? I don't have a price to give anyone, but interested if anyone has a guess before we start trying it. We've all been mesmerized into a magnetic stupor from the whirring sounds of a floppy drive. Yeah, that's right. Andy Magic says, no prize, no guess. Okay, right then. We shall offer the prize of the glory of having made the correct guess. There you go. Okay, so Prow is going to guess $1.16. So, yep. Any other guesses? Otherwise, he'll just get the glory right for having the closest guess. Okay, MPW was thinking 14. Yeah, okay. That'd be nice. Yeah. Look, you may as well be optimistic, so then if you're right, it's good. Andy Magic Knight says, okay, he's just going to guess 18. So he's going to be the pessimistic guess and decide that we're not going to get any improvement whatsoever. Cool. Well, we've got 3 guesses then. That'll do. Okay, Vulcan's going to go for 15. You can keep putting your guesses in as we go. So let's start applying the compensation. I've got to say that's actually better than I had expected. Have a look at that. So that first peak is now super skinny. This is fantastic. So kids can say, oh, I might as well claim for 13. Now the only thing that we can see is that the second peak, as we've seen before, is a little bit shifted to the left. So we do have the control for that. We'll see if that still works for us to shift that to the right. And I think that is working. That's looking pretty decent to me, I reckon. Okay, let's start winding the divisor down then. So we know that this is getting us 36 sectors at the moment. So it's just quite funny that it's getting 36, because before we were only getting 35 at that rate. It must be just on that limit, and a bit of luck as to whether it actually gets on there. But let's go. Oh, that's bad, isn't it? We might. Aha, okay, right. So, yeah, we can't do too much shifting of that pulse, the 1.5 at the higher rates. So 1.7, I think we can say is pretty good. Now, actually, our biggest danger is that that third peak has got a bit of a toe to the right here. Where are we? That one. I use the pencil of pointing. This is now the bit that worries me the most, right? Is that this interval here is a bit tight. But let's go 1.6. Still not looking too bad. Just trying to see whether that correction factor 1, 2. It's funny, there's a little extra peaklet to the right of the sixth one. That's fine, so long as the rest of them are good. So the question is whether this is actually helping any with this. That's clearly too much for the... Yeah, we're going to leave it at that for the moment. So that's 16 hex, and so that's getting us... what's that? So that's 32 plus 6, so that's 38 sectors per track at the moment. I'm just curious, so without gaps... It's 42 sectors per track. Remembering that a 1.44 meg floppy drive gets 18. So this is quite crazy. Right, okay, gaps back off. Okay, let's go to 1.5. And so, you know, I actually think we've got too much right pre-compensation happening. I think we can actually tune those. I'm actually going to go back a bit slower for a moment, because what I want to try and do is to tune the peak width as narrow as I can get it. We need to that's okay, but is 4 better? Okay, let's come back. So that was 16. Okay, so heard we were saying, my question is, why did no one do this back in the day? I think there was limited benefit in doing it. And also the floppy drives weren't as good. So this is possible with having good quality floppy drives that hold a stable motor speed. Ooh, I reckon 15 looks pretty good like that. I'm going to make a note there. And let's just trying to see what the better of the right pre-comp settings are going to be. So 15 is getting us 32 plus 9 is 41 without gaps. And that's getting us, so it's 32, 42, 45 without gaps. Do we dare and go down one more? Remember, so this is without the read post compensator to further help us. And now we're going to have to fiddle. Yeah, so I reckon that's a little bit too much. Oh. Yeah, so 14 I think is too much. So 15 I reckon is the current state of the art available to us. And that was with 0505 FE. Yay! Yes, it's Vulcan wins the prize of glory of having guessed the correct one. But remember, so this is without the read post compensator. So let's just see what that would mean. So remember, it will be detuned slightly because the other tracks, so typically I find taking 2 off for the average is about right, but it might be a bit less. So that would be 3.12 megabytes with sector gaps, and then 45 take 2 is minus 40 is 43, so that would be 3.44 megabytes. That has a nice ring to it, right? Say 3.44 meg floppy. And if we can do 84 tracks, 3.6 megabytes on a floppy at the moment. So yeah, we're getting up around that 3.5 meg mark. I think we can reasonably confidently say by doing the right pre-compensation with RLL. So that's really nice, right? So that's up from, we're saying, so with before it was either that, or if we do all the variations here, right? So that the first and third are without gaps, and the second and fourth are normal disk that you'd be able to write each sector to. So Andy Magic Knight is saying, are you not worried about data integrity at that size? I am somewhat, but we are not going to really know until we test it much more in earnest, and that doesn't make sense for us to do until we have the read post compensator in there to check. And we'll do some capture of these tracks in a moment as well to see really how bad the timing is, if we can do that cycle by cycle accuracy and get the updated gap info. Right, so that's what we had. So now we can do 138. Oh yes, because that was, yeah, right. Okay, so then the equivalent is 43 times 84, and then 39 times 84, 43 times 80, 39 times 80. So yeah, somewhere between 3.1 and 3.6 meg now looks possible. So yeah, I think we can say that yeah, it looks like more than 3 megabytes is possible on a floppy, which is pretty cool. And in all likelihood, more than 3.2 meg, which is all the FD4000 could fit on ED media, should now be possible. So yeah, that makes me happy. Right, so might do a little bit more hacking then on the read compensator, and then we'll do some more track captures and see how things are looking maybe while that synthesizes, or to feed into to simulation, because we will simulate the VHDL running for the gap compensator to make sure that it's implementing the algorithm correctly. But I'm just going to go get myself a glass of water and a brief stop. So back in 3 minutes. I've turned up the music while I'm out, and I'll be back in a couple of minutes. Okay, back again. Cool. Marauder saying this is awesome stuff and I'm learning a lot. Thanks, Paul. Old school coder is saying this is fascinating. Glad you guys are enjoying it. So let's have a bit of a hack at the. That's not the. Right, this is the one we want. At making this, right? So what we want to do, we'll do the output last there. So if gap valid in is equal to 1, then we need to shuffle everything down, right? So gap. Now I have to think about how we do this, right? So gap quanta 7 is equal to the gap quanta we can move down fairly obviously. That's you can do arrays in VHDL, but it often causes more trouble than it's worth, which is why I haven't bothered in this case. So gap quanta 0 will need to get set to what we estimate the quanta to be of the current gap that's come in. So we need to make the calculation of it before we can put it in there. So I'm just going to put 0 in there just for the moment. And then the gap times all need to get shuffled down, and then we need to add on to them the gap. So I think actually they're the more straightforward, because we've got, I just need to think this through, right, to get the algorithm right. And this is all a bit of a mess in my head a little bit at the moment as well. Because if we look at how we are doing this, where is it? We've got this. Yeah, so we need to divide the gap length by the data rate as well, and we need to get the remainder of that, because that's what we're doing here, right? So this is the gap. So this is what we're getting fed in, is the gap. We know the divisor. Now we can't do floating point stuff in VHDL, but ignore gap because we're not using it just at the minute there. So our 8 recent values are equal to the current quantized gap, what on earth have I, so what's recent getting set to? So and then we're taking off all of the older ones. So recent 0 is the oldest. Well, I think I'm just going to do it from scratch again and get my thinking there. Right. Hey Modrail, welcome along. And then we need to start doing the division. So that's the gap quanta. So the gap time is the time of arrival of each gap. So gap time 7. So this is the most, sorry, so 0 is the most recent one, right? So that will be gap size in. Gap time 1 is equal to gap time. Remember in VHDL things happen simultaneously. So this second statement is using the previous value prior to assignment happening here. So this is one of the things that bends people's head when they do VHDL. You kind of either get it or you don't, and at some point it will click. So now we can get the time ago of each gap. How long ago were the last 8 gaps? What did we quantize each of the last 8 gaps to be? Supreme Jerk 2087 is saying, I may well return to writing games and apps once I have a few of these MEGA65s in my hands. Yep, he hasn't written a game since he had a C64. That would be super. Would love to see that happening. We just love actually that people are finding the MEGA65 to be inspiration to do this kind of stuff, which is really nice. Okay, so that's all the simple stuff. So I'm going to reorder this. So I'll put the bit that is really straightforward up here. Okay. Now we need to work out what the quantization for the current gap is. Right. So this is where it gets a bit interesting, because we need to come up with the 8 different hypotheses to check whether we have exact binning on any of those 8 recent ones, and we need to calculate the average. So the average is kind of the easiest thing to calculate, and so I'll probably do the average first, because we can do that. So now the average needs to take into account, that's just based on the gap size in. So gross average, so this is before we have divided by the intervals per thing, right? So we can how do we do that? So we know when the pulses, because we have to benchmark it back. Oh, yeah, so this is where we have to take away the quantized gap from everything, right? So this is going to be a horrible, maybe I should do this with arrays so that I can do it over multiple clock cycles. Otherwise it's going to instantiate a bazillion adders, which is probably okay, but horribly, horribly inefficient. Let's think. So we need to get the duration of, so the most recent gap coming in is gap 0, right? And then the next most recent one is gap 1, and we know that gap 1 happened that extra time ago, and we quantized out 2 gaps. So we can need to take away the cycles per interval multiplied by the quantized gap from that. Just hang on a second, I think my son wants to ask me something. Okay, back again. So we need to divide out. Well, let's actually just start by working out what the current gap is, right? So quantized gap, what we want to say is gap quanta 0 is equal to gap size in divided by cycles per interval. That's what we want to say. This would be the easy way if we had hardware immediate division and floating point. Instead, we can work out the integer part using repeated subtraction, and then take a look at the remainder. Right. So I think that's what we're going to have to do. So really then actually the quanta is going to hold the integer part, and then we need to kind of remember what the all the leftover bits are, and maybe no, we'll just start by doing this. And so this is one of those things that's like it's super easy to do in C, right? You just do one line of code, right? Gap quanta 0 is equal to gap size divided blah blah. But in VHDL we can't do that. So we're going to start by saying gap quanta 0 is equal to 0. just going to call it bucket gap size in. Dividing, well, let's say state is equal to dividing bucket into gap quanta 0. So we need to make it a state machine, is what we have to do. Case state is when dividing bucket into that, and do something when others, and do something else. Right, and then we need to have a type state t is, I have to remember the notation for this. Type blah blah blah, that's right. So some things in VHDL are remarkably simple. So to make an enumeration, it's just like this. We just enumerate the things out. Dividing, right. And it's just other things that you want to do much more often are hard. Type state t, state right. If bucket is greater or equal to cycles per interval, then gap quanta 0 is equal to gap quanta 0 plus 1. Bucket is equal to bucket minus cycles per interval. Else, now it's just a remainder. So we're just going to ignore the remainder just for the moment. Signal bucket signed 15 down to 0. Okay. Is when always one statement long? Or do you, this is MW3P is asking, or do you mean can we do like when with different things? So you can, it's somewhat logical. With the pipe character, you could have, check for different states in there. And you can put as many okay, right. So remember what we're doing here. So case and when, in C I'll be writing this, switch state, case divide, right? This is how it would look in C. So VHDL in the, it was made by defense committees with the intention of being unambiguous so that you couldn't make design errors through not paying enough attention. And in their infinite wisdom, they made a bunch of things really confusing, like changing the terminology. They could have just said switch and case and gone, right, that's what everybody else does and that will be fine. But presumably some 5-star general decided that they couldn't understand that and that their preference needed to override thousands of software developers. Such is life. Okay, report. The remainder is bucket. Also note this this delight. Bucket has an unsigned number in it. I want to print it as an integer. This is how you do it in VHDL. You take the unsigned and you turn it into an integer, and then to print an integer, you can't just print the integer. You have to get an image of the integer into a string and concatenate it as a string with this horrible, horrible goop. Yes, and Herdway says, it sounds like normal military logic. Yes, my dad used to say there is the easy way, the hard way, and the army way. So, yes. Kidkin64 says, I'm used to case when, because I do a lot of SQL for work. Yeah, so that's fine. Okay, so now we have a incomplete design here that we want to start iterating on. So what we want to do is to make a test harness for this, which we are going to modify the existing test harness that I have that can simulate all of this stuff. So what it has an SD card IO in here, and it has the means to simulate let's simulate formatting, in fact, is what this is set up to do. So it does the pokes into the thing and controls it. So it's not perfectly right. Supreme Jerk is lol at the army way and says, I work in IT, so there's the right way, the wrong way, and the Microsoft way. Lol. Indeed. And M3WP says, int to str, same data types can add together, makes sense. Yes, there is a certain logic to it. It's just the verbosity of VHDL is the killer. It's really, really frustrating how much you have to type to make anything happen in VHDL. So, let's, and for another bit of fun here, trying to read a file, because what we would like to do is to be able to read a pile of interval lengths in from a file, and then feed them into this thing so that we can actually simulate that going on. That's a pain in the backside. Often what I resort to doing is just making an array in VHDL and calling it directly. Anyway, we'll make a copy of this as test read comp for read compensation, VHDL, and so here's another fun vestige of VHDL, right? You have to define the entity even if you're just going straight into an architecture, and even if it's completely empty. It's bizarre. Okay, so we only need a 40 megahertz clock. We do need cycles per interval. Yeah, so 81 equals DD, 40 equals HD, 20 equals ED. We don't care about track sectors, sides, or anything much else in there. Yeah, we're going to want a cycle count, that's fine. We don't need that. We're basically just going to take the bulk of it out. We do want to have a nice clock. I'll put the 80 megahertz clock back in just because it's easier than not. And then we don't care about that. Cycle count. Right. Okay. If cycle count is equal to, we'll say every 100 clock cycles. Actually, you've got to do less than that because we want to make sure that this can work. We'd like it to work with a data rate of as low as $10. I can't see us getting lower than that. That would already be stupid fast, right? That's twice the data rate of an ED disk, but on a HD disk that has, in theory, half the density capacity. So cycle count is equal to 0 again. Gap valid in is equal to 1. gap length in. Gap lengths, gap num is equal to gap num plus 1. Else cycle count is equal to cycle count plus 1. Okay, so that should feed in the gaps, and that should all be honky-dory. What we need to do now is I can never remember. So after the begin is where we put our things that we're calling in. Right. Entity work dot, what do we call it? Floppy read compensate port map clock 40 megahertz. Just having to type every signal name twice is really annoying as well. We want to enable it. Cycles per interval we want to set to cycles per interval. Gap valid in to gap valid in. Gap length into gap length in. And we want the outs of those as well. Last one doesn't have a comma because it's VHDL. Do it this way. Save some typing. And this is like Emacs, I can make a macro. Ins and outs. Okay, so we've got our signals, so that all looks good to me. Now we need a test MFM. So we've got another target like this. Read comp simulate we will call it, and we only have what did I call it? That was a test read comp.vhdl. I'll do it this way. Read comp files equals floppy read compensate. And we don't need that. This multiple lines of junk here is just to support different versions of GHDL, the VHDL simulator that run in completely different ways. Right, so let's try make read comp simulate. And yep, not surprising, we've got an error. Okay, 20 line 26. Yep, because I copied it from a line 49. Oh, hang on, so it's in the wrong file now, isn't it? Yeah, and the joy of VHDL, right? Variable name and then type comes after it rather than the almost universal convention of the other way around. If is expected instead of process, right? Which just means I've missed an end if. Yep, we don't have gap lengths and gap num. Yes, because what we want is signal gap num integer is equal to 0. Signal, first we need to make an array type. Type gap, let's call it gaps t, is array 0 to, I don't know, 10,000 of unsigned 15 down to, well, we can actually make it interior, we'll just make it easier to type. Signal gap lengths gaps t colon others 0. Right, and then we need to do gap lengths where we get that. Where was it? I'm in the yeah, because I'm in the wrong file. That's why I need to put this in there. Test to unsigned, because there is, it's all very strongly typed in VHDL. Okay, now next bunch of errors. Oh, gap length out, not. Oh, yep. Right, okay. Gap size in gap length in. Right. It's better. Okay. Gap quanta 0 because it should have a underscore. Can't match integer literal. Okay, let's type conversion to unsigned. No declaration for other. Oh, because it's others. Yay! Look at that. It's doing things. Right, so we're getting there. Git add source VHDL, test read comp source VHDL. Right, let's commit. Begin implementing read compensator. Okay. Cool, that does that. Where are we? Yep. So now we have a means of doing this. So let's just put, if the gap valid is in, right? Report ingesting gap of length. Make sure, yep, so it's ingesting a gap of length 0. Gaps of length 0, of course, are silly, but we can make that default to a gap length of something more than that. We'll just put 100 in just for argument's sake, right? Cool. Yep, so the remainder is 19. That sounds promising because we told it that cycles per interval is 18. Let's actually make it tell us what the whole number is. Gap is that typo. Okay, gap is 1, remainder 19. Cool. Now, why is it so it's ingesting gaps very rapidly after each other? So we need to do here gap valid in, so that we're only, that's better, we're only asserting it periodically. Cool. So now let's get us some realistic gaps. If we run that, I think somewhere I have this outputting the rare gaps. I fiddle with this so much. Yeah, so they're normalized. So here's our raw file. Okay, right. So it's the first, second, third, fourth, fifth column of our raw gaps file is the actual raw gap. 1, 2, 3, 4, 5. Right, so it's this column here. So this is our actual gap duration. So we can do cut field 5. Delimiter is comma. Right. That gets our gaps. And we want that from where did we see them? I can see. It's quite sad. I'm getting quite skilled at spotting these blasted intervals. So we want from 204, but we actually want to go back enough that we have pre-primed it by that point. So I'm going to go from, let's say, 190. We want to skip the first 190 of those. Okay, so that gets us that. Now we want to turn this into something that we can just feed nicely into the VHDL. So we'll use awk, we'll print the number followed by a comma, n++. If n is equal to 8, then we'll print a new line and put n back to 0. So this will put, maybe we can put 16 on a line, that'll be fine. So let's copy and paste all of this in. What I should do is, so which, so this is, yeah, $1.16 without, we want to do this with the right pre-compensated data, right? So I need to do a new collection of right pre-compensated data. Which will capture it. I'll do it for now with that because we've got it now there and handy. So I think that will work. Primary, yeah, so there's, oh, because I put commas in front, right, okay. And cycles per interval, we are going to say is, so it was $1.16, so we said it was 22. That should be then, right? You know, we actually can just, for simplicity, keep to consistent. Do it all in hex. I think we can do that to make it terminate. Nope. There's a way you can tell it to stop. Stopping VHDL simulation. Ah yes, assert false. I think it's actually as simple as that. Okay, now we've, oh yeah, that would help. Cool. Oh no, it still goes. It still goes to there. Gap is 4. Oh, because I set the others to be 100, right? I mean, it's still terminating when it gets to the end, but that's assert violation, assertion error. Why doesn't GHDL and stopping GHDL simulation? So there is a way to do this. that'll make it bomb out straight away. It's not the right way to do it, but it works. Okay, so what we have there now sorry, so M3WP has said, looks like Pascal, which I love. Yeah, unfortunately, it has some superficial visual similarity to Pascal, with none of the nice things about it and all of the horrible things. And string handling is worse than C, which is quite spectacular to achieve. Okay, so we can work out what the remainder is. Floppy read compensator. So if we look at that running, so we can see for these first gaps the remainder is 0, which is great, and then we've got some that are kind of going a little bit all over the shop. Somewhere, where is our... I think I've fluffed up copying the confused now, because we should have so here's these longer gaps. Okay, right, so we've got 57, 56. What are we seeing? Yeah, so we don't. Oh, fine. Okay, right. So now the trouble with these numbers that I've imported in, remember we can't, this is with the old capture that is doing one sample every 3 cycles. So what we need to say is times 3. So we're getting a 3, 7. Yeah, here we go, right? So here is our sync mark, 733, but 7 remainder 17, right? So it's almost 8. 337, big remainder, 2 big remainder, it's almost 3. 3, 7, 3, 3, so it's the same thing. So what I will do next with the quantizer is that we actually want to round the numbers and do that in a simple way initially, and to calculate what the error is for that. Yes, so that gets us the first step. That gets us then kind of what we already have, so that we can then start building onto that. Okay. And to do that, so we have our cycles per interval. If bucket, so this is our remainder. If it's greater than cycles per interval 7 down to 1, now then report round gap up to next. So I just want to do a quick sanity check on that. Right, so here's our thing, so it's going to round it up to the next one, which is good. Round it up to the next, 2, round it up to the next, yep. So that's all good. So, I'll have to stop soon and I'll do a few other bits and pieces. So let's do that. So that will get us the most recent gap, and so we'll do similar things with that added to the times of the previous gaps and work out what the number is, and then we have to take away the quantized gaps from the previous occasions and look at the remainder when we do that. So we're going to be doing this in parallel for 8 different offsets, and so I'll have to make it run fast enough, I'll probably have to do some checking, so we won't just take away a single lot of cycles per interval. We'll say if it's greater than that times 2 or times 4, that we'll pull off larger values of it as we go along, and for all 8 in parallel, and that will get us the number of gaps and the remainder. And we'll then look at those remainders, and we'll probably allow a little tiny bit of slop, like a remainder of 1 either way, and still have it deemed to be a whole number. Otherwise, we'll say that it's not eligible for voting for it being on an exact boundary, and then we'll have the whole setup for the average stuff. So I'll have a bit of a hack on that in my own time, but I think we will probably leave it at that point, I reckon. I'm pretty happy with that. We've bumped up again a summary from having 40 sectors per track up to 45, or 35 up to 41, which is really nice. So that's more than a 10% step up that we've managed to get, and I reckon we're going to be able to get hopefully another, push it to $1.14 or $1.13 or something instead of $1.15. With better capturing of the timing signal, which might have to wait till next Saturday, I reckon. Okay, thanks for tuning in. Hope it's been good fun, and we'll continue the adventure as we go along. Okay, take care guys, see yous.